Very good morning, dear students. I am Madam Prasanna and I am back to take the next session of power electronics, and today I am going to deal with the chapter number 9, switched mode converters. Switch mode power supplies I have already discussed in the previous sessions, which has totally replaced the linear power supplies. So today I am going to talk about the switch mode converters, and the first slide of this switch mode converter is going to deal with the different topics. So the topics which are going to be covered today is all the DC to DC conversions of the switch mode converters. So the first slide will contain DC to DC flyback converter. In the first slide, DC to DC flyback converter. Then I am going to talk about DC to DC buck converter. Then we will be moving on to boost converter, DC to DC buck boost converters, and finally I am going to talk about the comparison between the converters. So before I could actually move on to the actual converter circuits, I would like to tell something about the switch mode power supplies, which I already spoke. So the second slide is going to tell me a bit of basics of the switch mode converters. So in the basic operation, I am going to use choppers, which are DC to DC converters. You have already been aware of this. So it can be used as the switching mode regulators to convert unregulated DC voltage, a DC voltage which is not going to be regulated, to a regulated DC output. Regulation in the sense, the value of the magnitude of the DC voltage also I am going to tell about, and maybe the presence of noise, ripples, harmonics, whatever noise voltages also I am going to eliminate. And regulation is mainly obtained by PWM, which is pulse width modulation at a fixed frequency. So all the converters over here are going to deal with the changing of the on and off times of the switches, and switching device which is normally used here in these circuits will be power BJTs, MOSFETs or IGBTs. Okay. So the block diagram of a switching mode converter, I have given a very simple block diagram. Here you could make out you are having DC to pulse width controller, because pulse width modulation is the main. So DC input I am giving, I am talking only about DC to DC. Okay. So pulse width control is there, you are having a train of pulses, then the switch comes into effect. You will be switching on and switching off these switches for a particular period of time, maybe some more rectification in the form of a diode, and then you are finally having a filter circuit to get a regulated DC output. You could make out there is lot of change in the pulse train at the input to the output, which is almost a regulated DC output voltage. So these are the main components which all the switch mode converters are going to contain. So one by one, let us just talk about the types of the switching mode converters which we are going to deal with today. The first type is the flyback converter. A very special type of flyback transformer is going to be used, or inductor which is in transformer mode is going to be used. Then you are having a buck, which is a step down or a forward converter. The same terminologies are being used. Then you are having a boost or a step up converter, and finally a combination of both buck and boost converters. These are the different types of switching mode converters which are available. So first type, the flyback converter, it is a boost converter, means you are going to step up the voltage, and I told you the inductor is going to be split to form a type of transformer. It is normally known as a flyback transformer, so that the voltage ratios are multiplied. So automatically at the input you are having a low voltage, at the output you get a higher voltage, because I am talking it is a boost converter. And additional advantage of isolation is also there. So there is no problem of any personnel who are going to work with high voltages, there is isolation. And it can also be used for both AC to DC as well as DC to DC conversion with a galvanic isolation. Now, this is a special type of isolation which I will be telling between the input and any output. So, what does this galvanic isolation actually mean? Galvanic isolation is the principle of isolating the functional sections of the electrical systems to prevent current flow, and there is not going to be any direct conduction path. Okay, when I show you the circuit, you will very easily understand. Now, energy or information can still be exchanged. Please see, there is no direction, conduction path or connection wire between the two. Okay, that is why I will say transformer principle, because primary winding, secondary winding, there is no electrical connection between them, the two. So, same way in this also, energy can still be exchanged between the sections by other means, by introducing some energy storing element like capacitance or an inductor or electromagnetic waves, or even by optical, acoustic or mechanical means. But in the circuit of flyback converters, switch mode converters, I am mainly going to target on making use of a capacitance. So, galvanic isolation can be used, please see this point is very important, where two or more electrical circuits must communicate, but their grounds must be at different potentials. That is very, very important. So, I am not going to use a normal transformer principle. Normal transformers have the same ground. Okay, ground is similar and then they are at same potential, but in this galvanic isolation, the principle is the grounds must be at different potentials. So, a flyback transformer also is going to have two windings, and both the primary and the secondary circuits will be, the grounds will be at different potentials. Okay. So, with that principle, let us just look into the simplest what do you say, schematic diagram of a flyback converter. Please see, this is a DC source, then you are having a transformer like, okay, diagram, it is a flyback transformer, or you can say it is a split inductor, and then the switch, please see, it is not a normal switch, I am talking about the SCR, or I am talking about thyristor switches here, and then there is a diode, okay, and then you are having a capacitor, and here you are having the load resistor, at which I am going to find out my output voltage, get my output DC voltage. Okay. So, now the working of this circuit should be done for two modes. One is when the switch is closed, what happens to the current flow and what happens to the voltage, and then after some time when the switch is open. So, please see, switching mode converters, I am talking about how long the switch will be on, how long the switch will be off. Pulse width modulation is what I am dealing with. So, how long I am going to keep the switch on, how long I am going to keep the switch off. It may be BJT, it may be MOSFET, it may be IGBT as switches. Okay. So, let us see its working in those two modes. So, in the on state, you please see, on state means when the switch is closed, there is a switch. So, what actually happens here, switch is closed. So, directly the voltage source is being connected to the primary. So, when the switch is closed, the primary is directly connected to the input voltage source, that is what is very clearly seen, and the primary current and magnetic flux in the transformer increases. So, with the passage of current, the flux and the current is going to increase, and the energy is going to be stored in this transformer, in this winding. Okay, the voltage induced in the secondary winding is negative. Please see the dots. Okay, the dot here means it is positive and the upper side of the winding, and dot here means it is positive here. So, it is negative here. So, please see, voltage induced in the secondary winding is negative. So, it is a negative here, which means the diode is reverse biased. So, diode will never conduct, correct. So, please see, there is no conduction path here at all in the black portion here, there is no conduction path, but because of the galvanic isolation principle and because you are having a capacitor, this capacitor is going to get charged, whatever magnetic field voltage is going to be developed in the magnetic field here is going to be transferred to the electrostatic field of the capacitor. So, the output capacitor will supply the energy to the output load. So, there is a galvanic isolation over here in between, no conduction path at all is present. So, this is what happens in the on state. Now, let us see what will happen when the capacitor gets charged and when the load is getting the voltage. At that moment, if I switch off the second mode, so off state, what is going to happen? Now, please see this, whatever magnetic field was there, whatever current magnetic flux was there, it is going to drop because of the open circuit here. So, when the switch is open, the primary current and magnetic flux drops, but the secondary voltage at the same time will become positive. So, this upper end becomes positive, lower end becomes negative, okay, and that is why the diode gets forward biased. So, current flows through the diode, whatever is collected here in the magnetic path, it will flow through the diode and allowing current to flow through the transformer also. So, the energy from the transformer core recharges the capacitor, again the capacitor gets recharged and supplies to the load. So, even when the switch is open also there will be a voltage here, and when the switch is closed also there will be a voltage. So, this is how the flyback converter is going to be. And how is it going to be boosted? How is the voltage going to be increased? See, the control circuit will monitor the V out. Okay, the control circuit is there, I have not shown it, and this control circuit is going to control the duty cycle of the drive waveform to switch. So, duty cycle means the ratio of T on to the total time period, or T on into F. Please see, 1 by time period means frequency, you all know that, or T on into frequency gives me the duty cycle. So, this is the pulse width modulation principle which is going to take place in all the converters. Okay. So, if V increases, the control circuit will reduce the duty cycle accordingly so as to maintain a constant output. Please see, regulated output voltage I am talking about, and conversely a decrease in Vn will increase in load, will cause the duty cycle to be increased. So, the on period will be either increased or decreased depending on whether your input voltage increases or decreases accordingly. So, the relationship between the output voltage and duty cycle is not linear in this case, but it is hyperbolic. Okay. So, that is what is a flyback converter. I wanted to show the waveforms for you to understand the working more easily. Please see, it is a switch voltage I am talking about. So, when the switch is closed, voltage is 0. At that time there is a current in the primary, okay. At the same time there is no current in the secondary, that is what I have shown over here. So, trapezoidal also I can have, or I can even get a sawtooth waveform also, whichever I want I can. So, the main principle is when the voltage across the switch is 0, it is closed. At that time there is a current in the primary and there is no current in the secondary, you have seen that galvanized. Then after some time I will keep the switch in the open, okay, so that voltage maximum. So, at that time there is no current in the primary, but there will be a current in the secondary, and please see that current will slowly, it will decrease because of the discharging principle which is taking place through the capacitor also. So, this is how the waveforms are going to be there in the flyback converter for you to understand the operation in a better manner. Now, in the second type of converter which I have to talk about is the step down converter or buck converter. Now, what is the basic concept of the stepping down a DC voltage? I have shown very clearly in this slide. So, very simple circuit, you are having a switch, you are having a load resistor, okay. Then you are giving an input voltage and you want to find out what is the output voltage. So, please see, DC input, DC output, operation of the switch, switching off and on. Switch here means I am talking about a thyristor switch, it is not a manual on off switch, okay, right. So, please see what will happen when I on and off. Please see, this is on period, T on I have shown over here, okay, and this is the off period, T off, and switch duty ratio means duty cycle. I have already told you about this is D. I normally refer it to as capital D. It is the ratio of T on divided by the total time period. TS means T on plus T off. Please see, TS is T on plus T off here. And the average output voltage over here will be definitely, there will be a voltage only when it is on, and when it is off it is 0. So, average for the total time period, what is it? It is nothing but T on divided by Ts, total time period T on by Ts into the input voltage Vd. So, what is T on by Ts? I have already told you it is D. So, D into Vd. So, and much more, what you should all know is D is going to be a scalar, it is a value which is going to be 0 to 1, in between 0 to 1. So, always in this case output voltage is going to be lesser than input voltage by a ratio which is going to be suggested by D. So, the more time I am switching on, more higher range will be there, and more less I am switching on, more less of output voltage I am going to get. Okay, that is the basic principle. So, that is what is the basic principle. A buck converter is a voltage step down or at the same time current step up converter. Voltage is step down, current is stepped up to maintain the input and output power constant. Okay, and they are remarkably efficient, 95% or higher, because they in ICs they are used. So, they are very useful in tasks such as converting the main voltage in a computer. Computer voltages may be 12 volts DC in desktop, 12 to 24 volts in laptop, but processor requires only 0.8 to 1.8 volts. Okay, the ICs which are used in the processors. Okay, so 0.8 to 1. So, there should be a step down between 12 volt or 24 volt to 0.8 to 1.8 volt, and very high efficient way of stepping it down. So, that is where these buck converters are widely used. So, let us see what is the schematic of a buck converter. Please see, all these converters will be having a DC voltage source and there will be a load resistor. In between what is there is what is decided. You will be having a switch in the form of a thyristor, either BJT or MOSFET. Okay. Then you are having a diode. Okay. Then you are having an inductor. Please see, these are the major role is going to be played by these inductors. And if you remember, what is inductance? Inductance is the property by virtue of which it resists an instantaneous change in current. So, that is the property I am going to make use of in this converters also. Okay. And then you are having a capacitor to maybe filter, to smooth out the any unwanted AC in the DC. Okay. So, this is the schematic. Now, let us see how this converter works in two modes. Same way, when I switch on, what happens, and after some time when I switch off, what is going to happen to the voltage and current. So, please see the terminologies VI, V0, VL, IL. VL, IL means inductor current and inductor voltage, and VD means voltage across the diode. VI means input voltage, DC voltage, and V0 is the output voltage. Okay. So, when I switch on, please see, when I close the switch or when the switch is on, this is how the circuit is going to be. Red color is showing the current flow. So, when the switch is closed, the current through the inductor will begin to increase. Inductor, see, switch is going to close means from 0 to some very high voltage. So, sudden change in current, but inductor is going to oppose it. It is going to gradually increase. The current will gradually increase, then at the same time, because of the sudden change in the voltage and current, the inductor will produce an opposing voltage across its terminals in response to this sudden inrush of current. So, opposing voltage means voltage which is going to oppose this VI. So, there will be a voltage drop across the inductor. Okay. And this voltage drop counteracts the voltage of the source which has actually caused it, and therefore reduces the net voltage across the load. So, always the output voltage will be lesser than the input voltage by this voltage drop which is decided by VL. Okay. So, that is why it is a buck converter, it is a step down. During this time the inductor is storing energy in the form of the magnetic field, correct, because gradually the current is increasing and even the voltage drop across it is also increasing, and there will be an energy which is stored in the magnetic field. Okay. So, when this switch is closed, this is what is going to happen. What will happen when I open the switch? Now, at this instant, what is this diode doing? Please see, this is positive, this is negative. So, diode is reverse bias. So, that is why it does not conduct, right. In the next off state, when I open the switch, so please see, this is an open path. So, only path which is going to be there here is because of inductor is going to act as the source of voltage here. Okay. So, when the switch is open, then the VL itself is going to drive and V0 will be minus VL here. Okay. And please see, now at this instant the diode also is going to act as a path for conduction. Okay. So, if the switch is opened while the current is still changing, then there will always be a voltage drop across the inductor which is going to drive the current through the load. So, the net voltage by the load will always be less than the input voltage source always. So, over here output voltage will only be VL. Okay. So, that is what is the working in the on and off state. A buck converter operates in continuous mode. Now, normally I operate these converters in continuous mode. What does that continuous mode mean? If the current through the inductor IL never falls to 0 during the commutation cycle. So, I will be operating these converters either in continuous or discontinuous mode, but mainly continuous mode here means the current through the inductor never becomes 0. There will always be current will either move from lower value to higher value or higher value to lower value. It never becomes 0 during any part of the cycle. Commutation andre enu, when I switch off, when I open the switch, or when I switch off the BJT or the MOSFET which I have connected. Okay. When the switch is closed, the voltage across the inductor I told you is Vi minus V0. Why? It is counteracting the input voltage. So, it is Vi minus V0, and the current through the inductor is rising linearly. The inductance principle itself tells there is not going to be an immediate or instantaneous change in current. So, that is why the current will rise linearly, and the diode is going to be reverse biased when the switch is closed. Okay. So, there is no voltage drop. So, no current flows through it also, right. But when the switch is opened, what actually happens? Only the inductor voltage is going to drive the output. So, that is why VL is equal to minus V0, or V0 is minus VL, and the voltage drop across the diode also is going to be neglected, and the current IL is going to slowly start decreasing. Okay. It is almost discharging, I can tell, and it is going to discharge through the load and the diode, but the voltage drop across the diode is going to be neglected. So, now what is the equation which is going to tell me what is the relation between the output voltage and input voltage? Already I have told you duty cycle, and it is a scalar and its value ranges between 0 to 1, and the duty cycle is always a ratio of T on divided by T. T on means the time when the switch is closed or when the BJT is operating, MOSFET is operating, conducting, and T means the total time period, on and off positions of the switch. V0 is going to be the product of D into Vi. So, D means the duty cycle into Vi, and in this equation you always see D is the ratio. Okay, it is a ratio. So, in seconds it is. So, if I say for a period of 1 microsecond, if I am keeping the switch on for a few microseconds, so a few microseconds by 1 means it is a small value only. So, that is why the output voltage of the converter is varying linearly with the duty cycle. So, there is a linear graph between output and input, and duty cycle is always less than 1, it cannot be more than 1. That is why V naught is always less than Vi, and that is why this converter is always referred to as step down converter or buck converter. And example if I can give, if I want to reduce 12 volts to 3 volts, it is a ratio 3 by 12 which is 1/4. So, output voltage is 1/4 the input voltage, which means the duty cycle 25% if it is there, it is 1/4. So, that is why it's theoretically I can say it is a ideal circuit. Okay. So, I can always design circuits in such a manner by deciding how much of percentage of duty cycle should be there. 25% it should be on, 50% it should be on. 50% means 12 volts to 6 volts. Okay. So, this is how I am going to talk. Now, waveform I have very clearly shown only VL and IL over here. Okay. VL when it is on, VD minus V naught. VD here is the input and V naught is the output, and this is IL how it is varying linearly. When it is on, it is linearly increasing, when it is off it is linearly decreasing. It is a continuous conduction mode because current is never becoming 0. Okay. So, I have already given the relation V naught is D into VD, and power conservation principle, input power VD ID is equal to output power V naught I naught, that is what is shown in this. And I naught, I also told it is a stepped up current converter. Please see, I naught is a ratio of ID by D. ID means input current divided by D. D is a small value, so numerator is small value, which means the denominator is a small value, which means that numerator also becomes a higher value. So, that is why I naught is always greater than the input. Output current is always greater than input current, but output voltage is less than input voltage. So, this is what is the step down converter. Some more waveforms I am showing here, please see. Switch status on and off, then inductor current I already told you linearly increasing and decreasing. Then diode current, please see, only when the switch is off diode will work. So, that is why only in the off position of the switch you are having. Input current, only when there is the switch is on, input is current is there, and please see input current is discontinuous here. In the off position there is not going to be current. So, this is a very major difference between the other converters and this converter. Okay. So, that is about the buck converter or step down converter. The next type of converter is the boost or step up converter. So, boost converter is a DC to DC power converter, always having an output voltage which is greater than its input voltage. So, and it is a class of switch mode power supply, and what all it may contain, at least 2 semiconductor switches. So, diode also can act as a switch, transistor also can act, MOSFET can be there, IGBT can be there, and at least one energy storing element. So, I already told you it can be either a capacitor or an inductor or the two in a combination. And filters should be there to get a regulated output DC voltage, which is added to the output to reduce the output voltage ripple. I already have told you. So, that is what a boost converter. So, let us see how the voltage is going to be stepped up. A low input value voltage giving rise to a higher value output DC voltage. That is what is the boost or step up converter going to do. Simplest circuit, here I have not shown a capacitor, there should be a capacitor over here anyway. Supply is a DC, you are having an inductor. Now, the principle of the inductor always keep in mind. In this case, it is going to destroy the magnetic field which it is created. Then you are having a switch in the form of a thyristor, you are having a diode in the circuit, and finally the load. Okay. So, this is just a schematic of the boost converter. Now, what happens when I switch on, when I close the switch? Please see over here, at that instant of time only this circuit is working. The principle that drives the boost converter is the tendency of an inductor to resist changes in the current by creating and destroying a magnetic field. So, as soon as I close the switch, there is an instantaneous change in the current also, but the inductor will not allow instantaneous change, it will only allow linearly increasing current. In the boost converter, output voltage is always higher, and when the switch is closed, current flows through the inductor in the clockwise direction. I have shown it here, and that means polarity on the left side is positive, higher potential to lower potential current is flowing. So, that is why this is plus, this is minus. Okay? And when the switch is on, after I have switched it on, I should switch it off. Okay? During that period, what happens now? Along with this input voltage, the voltage drop across the inductor is also going to work, and that is going to drive this output. Okay, so that is why the two sources will be in series, causing a higher voltage to charge the capacitor through the diode. Okay, they are in series, they are working in tandem. Okay, so when the switch is open, current will be reduced as the impedance is higher. What current through the inductor I am telling, and the magnetic field previously created will be destroyed to maintain the current flow towards the load. Please see, this magnetic field previously, this side was positive, this side was negative, but now the polarity will be reversed. So, left side is negative and right side is positive. So, please see, negative positive, negative positive. So, that is why they are in series. The two sources will be in series, and that both the voltage will be making this capacitor to charge to a higher value, higher than Vi. Okay? So, that is why the voltage across the output will be greater than the input voltage. That is what is the boost or step up converter principle. So, again if I look at the expression, I am always talking about pulse width modulation, and please see, D is the duty cycle. Again it is the fraction of commutation period during which the switch is on. So, D ranges from 0, that is when the switch is never on, and 1 when the switch is always on. So, in between 0 and 1 only that value is going to be. And in a boost converter, please see, V naught divided by Vi is 1 over 1 minus D. Okay? And V naught therefore is equal to Vi divided by 1 minus D, and D is 1 minus Vi minus V naught. Okay? So, this is the formula, and in this formula please see, D is going to vary between 0 and 1. So, 0 and 1 andre when D is 0, what happens to the denominator? It is 1 minus 0, it is 1. So, V naught becomes equal to Vi, and if D is going to have some values, let us say 0.1, 0.2, 10%, 20%, 30%, whatever, 0.1, 0.2, 0.3, then 1 minus 0.1, 0.9, 1 minus 0.2, 0.8. Please see, the denominator is always lesser than 1. So, whenever I am dividing, I am going to get a higher value, correct? It will not be value Vi, it will be Vi, it ranges from Vi to infinity, because when D is 0, when D is 1, 1 minus 1 becomes 0. So, normally it does not happen. I do not switch on the switch completely for the time period. So, there will always be 90%, 80% when the switch is going to be on. That is why the duty cycle will never be 1. When does it become 1? When T on is equal to T. T on means the period during which the switch is on is equal to the time period. So, that means there is no off T off at all, which is not possible. That is why ideally speaking, output voltage will vary between Vi and infinity in this case, but infinity is not a practical case. So, that is why V naught will be varying between Vi and a higher voltage. So, the above expression always shows that the output voltage is always higher than the input voltage. Okay? That is why this converter is referred to as a step up converter. Now, the next slide is going to tell me Okay. Yes, this slide is going to tell me the same equations. Please see, I am given another circuit and I have shown the inductor voltage and inductor current. Continuous conduction mode only I am talking about. So, same thing, Vd into Id is V naught into I naught, okay, and V naught is Vd divided by 1 minus d, the same equation I have come back to in this, okay. And the circuit, how it looks like over here, please see, when it switches on and when the switch is off, this is how it is going to look like, okay. So, please see, this is the waveform, some more waveforms I am showing over here. Please see, switch status off and on, off and on. Input current is continuous in this case, please see, continuously. Input current means the current through the inductor. So, it is continuously increasing or decreasing, increasing or decreasing. Inductor only is going to act as the input current. Please see in this circuit, please see over here, inductor is connected at the input. So, that is why inductor current is the input current for this circuit, okay. So, that is why input current is continuous, it is continuous in this case. Then switch current, when the switch is on only switch current will be there, and diode again only when the switch is off diode is operating, okay. So, these are some of the waveforms which is going to tell me the working of the switch mode converter. So, the next type of converter is a combination of both. So, you could make out buck boost converter. I need to have a range of voltages, I need to have a lower and I need to have higher DC voltages. So, that is where this buck boost converter comes into existence. So, the buck boost converter, it is a type of DC to DC converter that has an output voltage magnitude which is either greater than or less than the input voltage magnitude. So, greater than means it is boost, less than means it is buck, okay. The two different topologies, both of them can produce a range of output voltages, from an output voltage much larger in absolute magnitude than the input voltage down to almost 0. So, that is why I told you, when I require a range of output DC voltage, regulated DC voltage, then I will choose the buck boost converter. So, let us see the schematic of this buck boost converter. Please see the same components, you can see the same components in almost all the converters except flyback. The buck, the boost and the buck boost, no, you will be having the same components but placed at different in a different combination. You are having a DC input voltage in all the three converters, it is there. You are having a switch, okay, in the converters the place of the switch is different. Then you are having an inductor, principle of the inductor to not allow the input current to instantaneously change, that principle also only is there. Then you are having a diode, and finally at the output in all the circuits you had a capacitor and a load resistance, correct. So, almost all the three converters, the same components are there connected in different ways, that is all. So, this is the way in which I am going to have a buck boost converter. So, let me see how it works in the on state. So, in the on state, you please see, when the switch is on, I am going to have the inductor directly in contact with the input. The input voltage source is directly connected to the inductor. So, linearly the current will increase, the voltage also will increase, and the magnetic field also will, the energy is stored in the magnetic field. Please see, at the same time this diode is reverse bias, so it does not work. So, energy is accumulated in the inductor, that energy is going to be transferred to the capacitor, okay, that energy is going to be transferred to the capacitor. There is no conduction path as such, okay. The capacitor gets charged and then there will be, in this, the capacitor supplies the energy to the output load, okay. So, that is when the switch is on, the switch is over here, it is on, it is closed, Okay. When I switch off, when I open the switch, only this portion is not carrying current, but already the inductor has been charged, it is storing energy. I do not say charge, it is storing energy in the magnetic field, and that is going to drive the current. Please see, a negative voltage is going to be there. Okay, please see the direction of current here. Previously it was in this direction, now it is in the reverse direction, and diode also is going to be forward biased in this. Okay, so that is how the current is going to be flowing through the load, and then the voltage is going to be generated at the load. Okay, so the energy is transferred from L to C and R. So C also is getting charged and R also is getting the current. Diode is also forward biased. So this is the working in the off state. Now the characteristic of the buck boost converter, how is it different from a buck, or how is it different from the boost converter? Please see, the polarity of the output voltage is opposite to that of the input. I already told you in the previous circuit also, polarity of the output voltage is minus, and the output voltage can vary continuously from 0 to minus infinity. And for a buck boost converter, the ratio of V0 by Vi is D divided by 1 minus D, where D is V0 divided by V0 plus Vi. So from the above expression, you can very clearly see the polarity is always negative. Please see why it is always negative here. Okay, D can always, it is going to have a negative value, and the waveforms in this case, please see, I have shown the waveform for VL and I have shown the waveform for IL, and it is a continuous conduction mode I am showing. Again VDID is V0 I0. Please see the circuit, how it looks like over here, how when I close the switch, inductor gets charged and magnetic field is created. At the same time, capacitor is going to drive the current through the load, and when I switch off, the inductor itself is going to drive the voltage. Okay, so IL is equal to ID plus I0 in this case, and I0 value also is given, ID V0 value is also given. So V0 is input voltage into the ratio of D divided by 1 minus D, and always this will be leading to a negative value. So that is why output voltage is always a negative value. Okay, so that is about buck boost converter. Now I have to compare these converters. Okay, and if I have to know about the comparison, I have to tell about these various characteristics. I have included a few of them. First characteristic, definitely output voltage. What is it with respect to input voltage, I have to tell. So in a buck, output voltage value is less than the input voltage value. In a boost, output voltage value is greater than the input voltage value, and in buck boost, the output may be less than or may be greater than the input voltage value, because it is a combination of both stepping down as well as stepping up, and it is a range of output values. Input current, I already showed you the waveforms slides and I have mentioned it. In the buck converter, the input current is discontinuous. Why? Because only when the switch is on, there is a current, input current, but when the switch is off, there is no current through there is no input current. So that is why it is discontinuous. And same time buck boost also, because it is already having a buck converter mode, so that means it has to be discontinuous in buck boost also. But please see over here, input current means the inductor current. In the case of boost converter, inductor is kept at the input. Immediately after the input voltage source, I have the inductor. So that is why the input current will be continuous in the boost converter. Okay. Then output voltage, I already talked about these formulae. with respect to the duty cycle. So, the first case Vin into duty cycle, that is for the buck converter, and for the boost converter it is Vn divided by 1 minus d, and for the buck boost it is minus Vn into d divided by 1 minus d. Please see negative, okay. The polarity of the output voltage is negative, so that is why I have written as minus over here. So, these are the values of the output with respect to the duty cycle values. Then what is the relationship between duty cycle and the output voltage? Only in the buck converter, because of this relay, you could make out V out is directly proportional to D. So, that is why it is having a linear relationship, okay. So, relation between the duty cycle and V naught in a buck converter will always be linear. So, you will be having a straight line graph, whereas in boost and buck boost it is non-linear. There is no linear relationship between D and V naught, okay. There is some other equation involved, so that is why it is non-linear, okay. And finally, polarity of V naught with respect to Vi. You already know in buck and boost it is non-inverted, means positive voltage Vi will give me positive V naught. So, it is non-inverted, whereas in buck boost plus Vi will give rise to minus V naught. So, that is why it is inverted, okay. And major comparison in the area of application areas, buck converter wherein I make use of it in computers and in laptops. I told you to drive the processors to give very less voltages to the processor, maybe up to 1.8, 0.8 to 1.8. So, that is where buck converters are finding high usage. Boost converters in almost all my lighting system, hybrid electric vehicles, okay, higher voltages to drive electric vehicles, okay, where I am not going to use diesel or petrol, I am going to use the battery and I am going to get high voltages to drive the engine. So, hybrid electric vehicles I can make use, and in almost all the lighting systems I make use of the switch mode converters. And buck boost, please see, mobiles for charging, in cameras, zoom in, zoom out, okay, wherein I require a lot of range of power, range of voltages. That is where I will make use of buck boost. So, this is the comparison table, and maybe one more comparison you can even tell is gate drives. Only in boost the gate is grounded. In buck and buck boost the gate will be floating, gate drive for the switches, okay. So, that one comparison also you can talk about in this case, okay. So, totally the 9th chapter has been covered. So, the probable review questions which may appear in your question papers list the types of switch mode converters. You may be telling about flyback, you may be telling about your buck boost and buck boost. Then what is flyback converter? Please see, I would like you to come to know more about the galvanic isolation. You may please check in the net and you may please read in the books, okay. Then what is a buck converter with the schematic diagram and how the voltage is reduced, and then operation of a boost converter, again how the voltage is going to be increased, the operation of it, then buck boost converter, and finally comparison between the three. So, dear students, always I wanted you to know something more. I wanted to see that you have some more knowledge about these various topics which I have been discussing. So, it is left up to you students to have a curiosity and to know more and more about this wonderful power electronic applications. The world over, the electronic revolution has happened because of the advent of these integrated circuits. So, VLSI, LSI, lot of components which are getting fabricated and myriads of applications. So, it depends on you students, your curiosity, your inquisitiveness, questioning, all those should increase and improve and make your learning process more and more enjoyable. So, dear students, hope you enjoyed this session as much as I did today, and happy reading and always keep smiling. Thank you.